For this video, we're going to be extending the work that I had previously done in R2. So if you want a little bit more detail, then go back and take a look at the video that I previously did regarding algebraic vectors in R2, and then that will give you a good foundation for what we're going to be looking at here in R3. The extension into R3 actually, as a result, this is a fairly brief lesson because we have covered so much of that other material already. In R2, we looked at the I vector, which had 1, 0 as its representation, and the j vector, which had 0, 1 as its representation. Now that we're talking about in R3, we've introduced that third dimension. So you can see the I vector has a very similar form, except for now we also, in addition to dealing with the x coordinate and the y coordinate, we also have to consider the z coordinate or the z direction for this vector. And so that's why we've had to add an additional dimension to each of these, the I and j vectors. So as a result, we end up with, for the I vector, x equals 1, and the other directions are 0. For the j vector, we have the y direction has a positive 1, and for the k vector, we have the z direction. And please keep in mind that all of these are what are known as unit vectors. They all have a length of 1, which in the case of these particular vectors, that's very obvious because the only value they have is 1. So these are known as the standard basis vectors in R3. And using these three vectors, you can describe any vector in a three-dimensional space. And since you can use these to describe any vector in a three-dimensional space, that means you can describe any point in a three-dimensional space. So if I have any given arbitrary point, ABC, the position vector has a vector component form, which is A, B, C, which looks very much like our Cartesian point form. We can also express this in terms of our unit vectors. So it has an x component of A, a y component of B, and a z component of C. We could break that up as A times the I vector plus B times the j vector plus C times the k vector. Similar to what we looked at in two dimensions. So once again, in R2, if we had a point AB, then the distance of OP was coming from the distance formula in two dimensions, which was x squared plus y squared, or sorry, I should have written that as the square root of a squared plus b squared. But in three dimensions, we have that extra dimension we have to take into account, and I am not justifying this to you, I am simply providing this to you, which is that the distance from the origin to this point P, which is ABC, or the length of this vector ABC, is simply a squared plus b squared plus c squared, all square rooted. Now, what about if I have 2 points? So if I have 2 points, the first one, I'm just going to choose 3 arbitrary coordinates, x1, y1, z1, and x2, y2, z2 for the point B, the coordinates of B. Then I can describe the vector between them in going from A to B. And if you remember this from what we looked at in two dimensions, to go from A to B, I actually have to do the vector subtraction in reverse. So in going from A to B, I actually start with the vector OB, and I subtract from that the vector OA. And I can do that using the vector component, the bracket notation, or I can do that using the direction vectors, I, j, and k, but ultimately I will end up at this result, which is it's going to be the second x coordinate minus the first, the second y coordinate minus the first, the second z coordinate minus the first. And just as I did on the previous page, if this is the distance vector from the origin to the point P, it turns out that the distance or the length of this vector AB has a very similar look to the distance formula, and the only difference is we have this extra third piece, which is due to the fact that we are in R3 and we have a third dimension. Otherwise, you may recognize this part as the distance formula. Not only is that the distance formula in R2 that we've talked about recently, but that's actually your distance formula from your grade 10 math course or whenever it was you studied the distance formula in geometry. It's the same thing. It's just it's just making use of Pythagorean's theorem. And the same is true here for this extra part. It's just we have to go through Pythagorean's theorem a couple of times because we're in a third dimension. Okay, so let's put these to some use, just as an example. Given these 2 points, A is 2, 3, 4, and B is -4, 5, -6. And so these are 2 points in R3. Determine each of the following. What is the length from O to A? Now, because I'm going from the origin to the point A, then that means that the vector OA has the same values in it as the original point A. And so the length of OA is simply equal to, again, the distance formula in 3 dimensions is just going to be 2 squared plus 3 squared plus 4 squared, all square rooted. And that works out to be 4 plus 9 plus 16. And so we get 25, 29. We get the square root of 29. For part B, what is the vector OB? And again, since it's from the origin to B, that just has the same form, -4, 5, and -6. And the magnitude, or the length, of the vector OB is equal to, I'm going to take -4 all squared plus 5 squared plus -6 all squared. And I'm going to take the square root of that. That gives me 16 plus 25 plus 36 all square rooted, which gives me 4177. So that is the square root of 77. That's the length of OB. Let me just double check my math there. 60, 71, 77, yep. C asks me, what is the vector AB? So the vector AB, in order to go from A to B, I actually start with the vector OB and I subtract from it the vector OA. Now I could do this a couple of ways. One way I could do it is just using the vector components in the bracket form. So OB is -4, 5, and 6. -4, 5, and 6. And I'm subtracting from that the vector OA, which I've got written here. That's 2, 3, and 4. And there's nothing saying that I can't stick with this notation. So I get -4, and you can see I've got a minus here. Now, how you do this, I'm going to show you. You've got a couple of options in case that wasn't clear to you. If you prefer -4, 5, and -6, I've already made a typographical error there, so that's supposed to be -6. I'm glad I caught that. And if you want, you could make this addition, and then you would change all of these to the opposite signs. I wouldn't bother doing that, but I want you to understand you have that option. So regardless of which of these two you're comfortable with, I would probably just stick with this line right here. And so I would say -4 minus 2, that gives me a -6. 5 minus 3, that gives me a 2. And a -6 minus 4, that gives me a -10. Or, so I'm just going to go over here, and I'm going to say, or, what's the other way I could have done this? I could have said that's equal to OB. I'm going to actually write as negative 4I plus 5J minus 6K, and then it's going to be minus bracket 2I plus 3J plus 4K. And then I combine those together, and I'm going to skip doing this middle step this time. I'm going to just expand or distribute this negative sign into this bracket as I go. So I have negative 4I minus 2I is negative 6I. 5J minus 3J is plus 2J. And negative 6K minus 4 more K is negative 10K. And this, of course, if I wanted to, depending on the form that I wanted to use for my final form, this is perfectly good, this is perfectly good. And if you're wondering what form you should leave it in, well, look for a form that is being used consistently in the question. And if the question is flipping back and forth between things, or in this case, the question only ever gave you values in terms of the points, so then it's really up to you on how you represent this. So both of those are correct answers for the vector AB. And then finally, part D, I believe, just wants to know how long is that vector that we just found? How long is AB? So the magnitude of AB, or the length of AB, is just, I'm going to take negative 6 squared plus 2 squared plus negative 10 all squared. And I take the square root of that whole thing. So I end up with 36 plus 4 plus 100 all square rooted. And that ends up being 140 square rooted. And I didn't do this in advance, but perhaps I should have, because I know that 140 is the same as 70 times 2, which is the same as 35 times 4. And then 35 is just made up of prime numbers because 35 is just 5 times 7. So the only perfect square here I have is 4. So this is actually 2 square root 35 if I reduce that radical. And that's it for this lesson. The remainder of other key concepts would be contained in the lesson on R2, and then you've got a healthy amount of homework there to let you continue to practice these different skills in R3.